So in this example, I have a function t from r square, a plane, to r square, a plane, that projects a vector onto the line y equal to 2x. So I have just the r square plane, and I have a line y equal to 2x. Now, what this vector does, what this function does, is that if I have some vector, whatever vector, v, the image of this vector is going to be its projection onto the line y equal to 2x. So I project this guy onto the vector y equal to 2x. Now this is going to be the image of my vector. So my orange line, this is y equal to 2x. Now then, I wonder if this guy is a linear transformation. Well, to check if something is a linear transformation, there is something there is just two things that we need to check. I just need to check if t of u plus v is tu plus tv. So this is straight from the definition. Plus tv. And then I need to check that t of a v. Right. Let me check that av, is a times t of v. Okay, so let's take a look at this real quick. So let's say if I have a vector u and I extend it by a vector v. So let me actually use a different color here. Let's see, this is my vector u, and I extend that by a vector v, something like that. Okay. So u plus v is gonna be I'm running out of color. U plus v is gonna be the teal vectors here. Okay, this is my u plus v. Okay, so let's see what is the t of u, t of v, and t of u plus v. T of u is gonna be the image of u onto the, it's gonna be the projection of u onto the orange line. So if I draw the perpendicular line here, t of u is going to be this vector here. So this is going to be my t of u. What about my t of v? My v is this little vector here. So the image of v onto the orange line, in the projection of v onto the orange line, is going to be this little vector here. So this is my t of v. And my t of u plus v is just going to be the image of the whole u plus v thing. So it's going to be my teal vector here. This is my t of u plus v. So it seems as if, well, t of u plus t of v is indeed t of u plus v. And it kind of makes sense. You can think of this whole projection thingy as just a shadow. So you can think of there is a light going there is a, let me actually use color. That would make sense. There is a light in this direction, and it casts a shadow of my vector onto the line, onto the orange line. So if this is my my object, then the image would be the shadow of that object. So that makes sense. Now then, I look at the same thing here. If I have two objects, so I have my first object, my purple object, and I extend that by the green object. The shadow of the whole structure is just gonna be the whole shadow. If the shadow of the whole structure is just gonna be the shadow of the purple object extended by the shadow of the green object. So that would make sense that the shadow, the shadow of the structure is just the sum of the shadow of the two. So this guy, I have it. It makes sense. Let's look at the second one. If I multiply my vector by a scalar, what would happen to its shadow? Okay. So let's say this is my vector u. So au would basically be another vector that goes in the same direction. So let's say that's my vector u, and this is my vector au for some constant a. It could have gone in the opposite way as well, but that's fine. So let's say that's my vector au. Now then, the projection of u onto the orange line would look like this. And the projection of the multiple of u onto the orange line would look like this. So this is my t of u, and the blue thing here, this is my t of au. And it would actually seem as if this guy, my thing here, is actually just a times bigger than my original thing here. And that also makes sense in the shadow metaphor. If the object gets 2 times bigger, then the shadow should have got 2 times bigger. If the object gets a times bigger, then the shadow is gonna get a times bigger. So indeed, this thing is a linear transformation. So my t, this is a linear transformation. And because it is a linear transformation, it actually has a matrix form. So that means there is actually a matrix that whenever I multiply this matrix to a vector, let's say a vector AB, the product of this multiplication, this is actually going to give me a projection of that vector AB on the line y equal to 2x. So think about it. There is actually a matrix that when I multiply that matrix by AB, the product is going to give me the projection of AB onto the line y equal to 2x. Now, without linear algebra, finding this matrix would be pretty hard. But we knew from before that if I want to find the matrix thing here, if I want to find T in matrix form, what I have to do is just find its 2 columns. The first column is actually just going to be T of 1, 0. Wherever 1, 0 goes to, I write that here as my first column. And then the second column is just going to be T of 0, 1. Whatever my 0, 1 goes to, just write that in the second column. So, I just need to find out what is the image of 1, 0 and 0, 1 and write that as my first column and second column here. Okay, let's actually kind of draw a picture here. This is my 1, 0, this is my 0, 1, and here's my orange line, the line y equal to 2x. Y equal to 2x. Okay, so the image of the vector 1, 0 is gonna be this little guy here. So whatever this green guy is, I just have to write its numerical value into the first column of my matrix. So how do I find the numerical value of my green guy here? Well, you can use the geometrical properties of the projection to find the value for the x and y coordinate of my green guy. Or I can just go ahead and use the vector projection. One of the vectors that lies on this line, I'm just gonna pick the basic one, this orange vector, because it's on the line y equal to x. I'm gonna call it 1, 2. I mean, it's the vector 1, 2 because y equal to 2x. So I just need to find the projection of 1, 0 onto 1, 2. Whatever the projection of this guy onto 1, 2 is, it's gonna be the value of my green thing. So if you don't remember, if I want to project the formula for the projection, if I want to project the vector v, so this is called v, if I want to project a vector v onto a vector u, the formula for that is actually just gonna be, okay, now I think I'm gonna have to use, okay, it's gonna be v dot u over the size of u squared times u. Okay, so let's actually do the math here. So the projection of 1, 0 onto 1, 2 is gonna be the dot product of the two. It's gonna be let's see, 1, 0 dot 1, 2 over the size of 1, 2 square times 1, 2. Well, let's see what this gives. This dot product is going to be 1, the size of 1, 2 square. The size of 1, 2 is going to be the square root of 1 square plus 2 square, which is square root of 5. I square that, so I get a 5. So it's going to be 1/5 of 1, 2. So that's going to be 1/5 and 2/5. Let me actually write 0.2 and 0.4. So this is going to be my first column. 0.2 and 0.4. Okay, let's move on to the other one. Let's see, what color should I use? Okay, so I have my, if I project 1, 0 onto the orange line, this is the vector that I'm gonna get. So something that looks like the blue vector here. To find the numerical value of it, I'm just gonna use the same formula again. My v now is gonna be 0, 1. So it's gonna be 0, 1 times dot product with 1, 2 over the size of 1, 2 square times 1, 2. Okay, so this guy is a 2 on the top and a 5 on the bottom, and then 1 and 2. If I multiply 2/5 times 1, I get 0.4. And then if I multiply 2/5 times 2, I get 0.8. Voila! So this is actually the transformation matrix for the linear transformation T. For whatever vector AB, if I want to find out what is the image of it, what is the projection of it on the line y equal to 2x, I just have to multiply AB by this matrix 0.2, 0.4, 0.4, 0.8. So this thing here is the linear transformation T in matrix form.